Okay, hi everyone. I'm Nico from UC Santa Barbara, and this is joint work with Burak Kadron, who's sitting over there, Lucas Bang and Tefik Bultan from the UCSB Software Verification Lab in the context of the DARPA STAC program, which is a multi-year program. It's a 4-year program with the goal of improving the degree of automation in the detection of 2 kinds of vulnerabilities in software. We worked mainly on these ones. And this is what I'm going to present today. So as you all know, since you're sitting here, it's been a couple of decades since people have been studying these kinds of, EM attacks, power analysis attacks. More recently, other phenomena of shell data at the CPU level has been exploited with great success. But all of these are examples of side channels in hardware, right? We are interested in side channels in software. For instance, if you could measure the memory usage of a process over time, you may be able to extract information about things that are happening at certain points that perhaps you should not be able to know. Or if you could precisely time how long a method takes to execute or how long a loop takes to execute, you could infer something about the variables involved. Now, this kind of precise local timing is a strong assumption. So in our attack model, we're going to assume that no such local measurements can be performed. In fact, we target multi-component systems, such as client-server or peer-to-peer or other kinds of architectures where you have multiple components joined together by network links. So all of our side channel measurements are going to be performed on the network level, which means you're going to have packets flowing back and forth, TCP, UDP packets. Of course, TLS encryption is always used in these systems to hide the payloads from eavesdroppers. But still, typically, some characteristics of the packets can be seen despite the encryption. This is application dependent, whether an application decides to pad that or not. TLS doesn't impose anything on that. So in our attack model, what we're going to assume, to summarize, is that the main channel is the unencrypted conversation intended for the legitimate user, and the side channel is going to be the size, time, source, and destination of each packet. And that's all we're going to work with. Right? So Profit is going to black box profile the whole system as is, without any modifications, and try to find features that can be used as side channels to extract information and quantify how strong those leaks are. So what do we expect from the user? The user has to, so the Profit user has to choose an interaction. For instance, let's say, log into a system, upload something, do something, get something, something like that. And this is going to be repeated over and over. We also need the user to provide a set of valid inputs for that interaction and to choose a secret of interest, which could be, the salary of an employee or the age of a patient or whether a patient has a certain condition or, it's one secret that we are interested in knowing whether it's being leaked or not. So Profit is going to run the interaction repeatedly over all the inputs, capture all the traffic, look for correlations, and output a ranking of the top N features that leak most information about that secret. This is the idea. So let's look at a very, very simplistic example. Imagine that in a court system, a clerk is logging in and uploading a case file with evidence and the judge ruling and the results. And the secret that we care about is the verdict, guilty or not guilty of that case. So if we let that happen several times, and we capture the traffic for each, and of course, we know the verdict because we are profiling the system, right? So if you did, so you know the verdict for each, the secret for each case, but what you don't know is the structure, since this is black box. What do these packets mean, et cetera? So after a lot of painful wire sharking by hand, you may end up inferring that, packet 17 tends to be smaller for not guilty and bigger for guilty defendants, right? So if you run this a couple thousand times, you will end up with a couple of distributions for each of the secret values. The size of packet 17, which is this feature, has a certain probability distribution so that an attacker armed with a profile like this, in the future, if they saw a packet trace on the wire and they saw that packet 17 was a certain size, they could know whether the defendant is guilty or not guilty. Of course, there could be some area for confusion, but this feature, size of packet 17, definitely leaks at least partially the secret, right? Now, why that feature? Because it could have been this other the size of this packet, or the time between any two packets, or the total size of any subset of packets, right? There are many things we can look at. And in fact, there are, it's an astronomical number of features, and there's no way that you can analyze all of them. And depending on what features you look at, one feature may give you complete confusion, another feature may give you partial leakage, and if you're lucky, you may find a feature that gives you full or almost full leakage of the secret. So Prophet does this analysis over many features, and it outputs a ranking that says, look, the most leaky feature is size of packet 51 from this machine to that machine, and it leaks this much. Next is that, etc. That's the basic idea. In fact, these numbers in percentages are a simplification. We quantify the leakage in bits using entropy. I suppose many of you are probably familiar with Shannon entropy. This is a way to measure the information content of a random variable, which is very similar to the notion of uncertainty, right? Because there is no information in certainty. We use Shannon entropy as a measure of the initial uncertainty. So how much uncertainty about the secret is out there when you haven't observed anything yet. Then we use conditional entropy as a measure of the remaining uncertainty after you have performed a number of observations on a feature. So that probability distribution is something that we don't have, but we estimate it based on all the values that we profiled on the system, right? Finally, we subtract, so from the initial uncertainty, we subtract the remaining uncertainty of the attacker after having observed the feature, and we end up with what's called mutual information, which is our definition of leakage, which is essentially how much information could an attacker gain about the secret by observing this particular feature and its distribution. Of course, we do this for each feature, right? There could be many thousands of them, and we do this for each one. Now, regardless of whether you use mutual information, conditional entropy, classifiers, neural networks, whatever you use to learn about correlations, the set of features that you consider, so the feature extraction problem, is the central problem here. So, what was that? We have a library of simple features that we use because they're simple and because it makes sense to try them. So we systematically try these, such as, the time between each pair of adjacent packets, etc. But it turns out that especially when there's variable length content involved, misaligned packet traces cause a lot of trouble with, statically defined features like that. So after realizing that the shortcomings of this library was due to this, we came up with the idea of using some smart alignment to extract more meaningful features. So I'm going to show you a visualization where each packet is represented by a square that shows its size and direction, so that when we capture one whole interaction, we get a packet trace that looks like this, okay? So this is a multi-user chat system. The interaction is going to be someone logs in from some part of the world, sends some message to some other user, and the secret is where was the person, where did they log in from? So for instance, Joe logs in from Paris and sends, hi, how are you, to Mary. Peter logs in from Berlin and sends some other message to Joe, etc. And every time you run the same interaction, you get a similar trace with different variations in it. So if you run this 60 times, you end up with a collection of traces. And now if you look at the standard basic features, for instance, the packet number 1 of each trace, well, that's constant, so there's no leakage there, right? Packet 17, which was lucky before, is not constant, but if you plug it into the entropy formula, you see also that there is no leakage from this as well. And in fact, if you look at every nth packet for every value of n, there's no significant leakage from any of them. Now, there are some recurrent patterns across that appear in most or all of these traces, and they're really beckoning to be aligned in some way to try and make sense of the data. So we tried aligning one of these recurrent patterns to see if we could get better feature extraction that way. But it turns out that there are other, alignable features that you could consider, or, even a third one. And each of these 3 alignments has its pros and cons, right? In each case, you see some parts became neat and aligned together and very orderly, where other parts which could be alignable remain chaotic, right? So when you look at the whole picture, you think, well, maybe if we inserted some gaps, we could find a way to maximize the overall alignment of all alignable patterns while keeping the total error low. So this is a very hard problem, and it's a very well-known problem in computational biology, where this is called MSA, and it's used for DNA sequencing, with our friends were talking about. Not in synthesis, but in sequencing, probably the inverse process. This has been studied for a long time in the bioinformatics community. And so we thought, what if we encode our packet data in some way that we can leverage these MSA algorithms and then add some of our own heuristics to split the result into meaningful phases. So that leads us from unaligned traces to traces that make more sense. Here, for instance, you can see orange packets are full packets. They have like full information, they're as full as they can be. So that streaks of orange packets followed by one packet basically represent objects that are larger than what one packet can contain. And our heuristic separates this, in this case, into 10 different phases. And as it turns out, when you sweep these features, the size of this particular packet does leak the secret in form. This is due to a blurb, something like a little paragraph that says, the city of Tokyo is the capital of Japan, and it's a beautiful city, blah, blah. And those paragraphs can have different sizes for each of the unique cities, so that provides you a signature and gives you leakage. The problem is that that leaky feature is all over the place in the original traces. So it doesn't really have a name. It's not the nth feature for any value of n, right? It's very hard to pinpoint. It's hard to pinpoint automatically. It's impossible to pinpoint using Wireshark. So, well, I mean, not impossible, but very, very tedious. So once you align things in a more meaningful way, that gets a name. Now it's packet 2 of phase 6. And our ranking gets enriched by these more meaningful, for instance, now you could consider the total size of each one of the phases or the maximum size in each one of the phases, so you have more richer features to work with. This is from an unrelated example where we have 12 different secrets and profit. So without phase detection, the best it could find was the duration of the whole trace, which leaked about 40% because there's a lot of overlap. Whereas with phase information, a better feature is the duration of phase number 5, which provides a lot more isolation. And in fact, the top feature detected by Profit for this example is the time between 2 particular packets in phase number 5, which gives you full leakage of the secret. So, well, this was not just the merit of Profit, it was also the merit of very smart people like Shireen and Burak working on these problems with us there. But I think Profit helped us get really good results in the challenge. I was there for engagements 4, 5, and 6 in DARPA in Washington. And for side channel problems, we were often the top team, typically always within the top 3 teams, depending on what metric you look at, because they have several metrics to classify, to rank the teams, false positives, false negatives, etc. One interesting thing is that after each engagement, DARPA would give us the results, so the correct answers. And it turns out that the leakage reported by Profit for the top leaky feature that Profit could find is usually consistent with the presence or absence of vulnerability as reported by DARPA. So that, if you look at how much the top feature leaks and what DARPA says we should expect to find, it usually matches. Another interesting thing is that after DARPA gave us the final answers for each of the engagements, we were able to much easily, by hand, manually find the best possible feature for each of the cases. And in general, when there are, in the cases where there are vulnerabilities, the top ranking feature reported by Profit is consistent with the best feature that we could find by hand, especially when there is a vulnerability. When there isn't, Profit finds other stuff, which also sometimes surprises and led us to interesting conclusions. So as ongoing work, after this paper, we are now working on adding feedback-driven mutation to Profit so that you can mutate more inputs and create more inputs and improve the quality of your ranking quantification. And there's also, and the stop criterion to know when your ranking is good enough. And there's also some aspect of noise modeling necessary because, especially with time features, there's non-determinism due to the noise in the network. There's also some non-determinism sometimes in the system. And so you need to basically repeat the same input many times so that you can model. So, you know, collisions become overlaps between these noisy distributions. So we're working on automated estimation of how many times to run each input so that it's, you know, cost-benefit-wise, maximally beneficial. This is all that I had to show today. Thank you very much for listening.
Hi, very interesting work. Did you also consider or observe packet reordering?
Yes, we did. So many of these examples, we are now using T-Shark in ongoing work. So this work was conducted on the DARPA reference platform, which provides some level of noise, but it's sort of carefully, you know, you have some level of risk for reordering and duplication of packets and retransmissions. We get some events of that, and they just die out as outliers in the general scheme of things. You know, the MSA alignment is tolerant enough that it can deal with a couple of those cases, and we just scrap them out as outliers. In a live setting, if you go to the live internet and you have that level of packet reorderings, we've been using T-Shark, which does some analysis of packet, you know, reordered packets and duplicate packets and retransmissions and try to get rid of those. But mostly, I think we are trying to assume a circumstance where you have more normal than abnormal traces, and you can use them to find out which ones are the abnormal ones and rule them out. It's profiling work, you know, so you can, if you discard 5% of the sample, that's not a great deal.
Thank you.
Hello, nice talk. So Stanislav Mišković from Splunk. What I wanted to ask, in the end you were showing that you are including feedback as this future work. So this work is also very, very nice for, you know, feature engineering, feature selection in an automated way. But could you comment on how tied are you methodology-wise to the input? Because you ask for the inputs to qualify what's okay and what's not. Could you delay that such that in a feedback you would start kind of discarding things instead of ahead of time?
You start, sorry?
Discarding things or what is useful and what is not.
Right. So in the version of Profit that is reflected on the paper, on the NDSS paper, the whole input set was provided by the user, either by extension, just by giving you a set, or by giving you a generator and a bunch of parameters, you know, to generate the inputs. As you say, that is very you know. Quantification heavily depends on the inputs, right? If your input set is very bad, your quantification is going to be very bad. So the approach we have now, what we're investigating, is this feedback-driven mutation based on mutators that preserve validity, so that, you know, we ask the user to provide, these are some examples. You know, for each application, we ask the user to model the input space using mutators. And the main problem here is that we wanted to preserve validity of the inputs, as opposed to fuzzing, where you can just, you know, just shoot random stuff at the system. These are systems that take a while to boot. If you break the system with an invalid input, you bring it down, you need to wait for it to come back. So our main limitation is how can we generate more inputs in a way that is robust and that preserves validity, and we worked within those constraints, right? So we offer class hierarchy that makes it easy for the users to provide, you know, these mutations from valid input to valid input, and that's our approach right now. It is, I mean, it is tied to a certain methodology, but I think it stems mostly from the fact that we do not want to venture. So each execution here usually takes several seconds, so we don't want to venture into the realm of invalid inputs, which really brings down